Welcome. This is the fourth and final video for Chapter 6 on kinetics in thermochemistry. So at the end of the third video, we were talking about factors affecting the rate of reaction, and you need to increase the number of collisions, and specifically you'd like to increase the number of successful collisions by changing the orientation or the energy or both orientation and energy. And there's 5 ways this can be done: temperature, concentration of reactants, particle size of reactants, pressure, or using a catalyst or inhibitor. So let's take a look at each one. Increasing temperature is going to increase the rate of any reaction because it's going to increase the kinetic energy. So cold will slow a reaction rate, whereas increasing the temperature will increase a reaction rate. And it has 2 effects. It increases the total collisions, and it increases the number of collisions with enough activation energy. And one question IB always asks is, which one has the bigger effect? Well, it's the increase of particles with enough activation energy, because it doesn't matter how many collisions you have if they don't have enough activation energy. So anytime you can increase the number of collisions with enough activation energy, you will see a positive effect on reaction rate. And typically, doubling the temperature in Kelvin will double the rate. The effect of increasing temperature then is often asked to be explained using a Maxwell-Boltzmann curve. So down below, temperature 1 is the initial lower temperature, and temperature 2 is a warmer or higher temperature. And the changes that you should notice in the graph is that basically the graph kind of tips over to the right. So the peak is a little bit lower, but as it runs out then, the energy of the molecule stays a little higher as you move out to the right. So the area underneath the curve is the same. So the number of particles is the same, but you have more particles with more energy, and specifically you have more particles with energy at or above the activation energy. Second factor is concentration versus rate, and increasing your concentration of reactants is going to increase the rate because when they're more crowded, they're going to have more chances of colliding. So increasing concentration rate is increasing the frequency of collisions, and thereby then increasing some of them with enough activation energy. So it's like a crowded versus an empty hallway. There's going to be more bumping the more crowded it becomes. So the greater concentration, greater collisions, greater rate. Increasing the amount or volume does not increase the rate. This would just be like having a longer hallway with the same amount of crowding. It's not going to increase the number of collisions in any one area of that hallway. It's just going to be a longer hallway for it to occur in. So overall, you eventually will get more product, but you're not going to get it any more quickly. And a concentration for a solid is indicated by its density. So typically, you can't change the concentration of a solid. The next factor to consider is particle size or surface area of your reactants. If you have a solid reactant and you divide it into smaller pieces or decrease the particle size, you're going to increase the reaction rate because your increased surface area allows for more contact or more frequent collisions between that solid and the other reactants. So it increases the probability of successful collisions. So in many solutions, stirring can help decrease the particle size and increase the rate as well. But think of it as like using small pieces of wood to start a fire instead of a thick log. If you throw on sawdust, it will flame up very easily. Whereas if you have, a big thick piece of wood, it's going to be much harder to get it to catch. And in fact, this idea of surface area or dust is responsible for a number of industrial accidents when fine dust tends to build up, like in coal mines, grain elevators, and flour mills. So it can be a dangerous thing as well if you're in one of those businesses, but increasing surface area is definitely a way to increase reaction rate. Pressure. If any of the reactants are gases, then increasing pressure will increase the rate because it's going to force the particles of the gas closer together and increase collisions, just like increasing concentration. But if the products are gases, it can actually increase the reverse rate or slow down the forward rate. So this is you're looking for the reactants to be gases, increasing the pressure to force more crowding. If your reactants are all liquids or solids, then pressure is going to have little effect because liquids and solids are already crowded about as much as they're going to get. And then finally, a catalyst. A catalyst is a substance that increases the rate of reaction without itself undergoing a permanent change. And what a lot of people don't realize is that throughout the reaction, remember, many reactions are a series of smaller reactions, or this reaction mechanism, a series of steps. And during those steps, the catalyst is changed chemically, but then by the end of the reaction, it is reverted back to its original form. So it doesn't undergo a permanent change. And what catalysts do is they provide an alternate path for the reaction to follow, which has less activation energy associated with it. So it changes the enthalpy diagram because it brings the peak down, but it has the same effect on making bonds and breaking bonds. So it decreases both sides of the graph equally. So that means the heat of the reaction, or your enthalpy, is going to be the same overall. It's not going to change the equilibrium. So it's not going to change the amount of product made. It's going to have an equal effect on the forward and reverse reaction. It's just going to increase how quickly it's made. So we can also look at the Maxwell-Boltzmann curve with the catalyst. And instead of changing the curve, what it does is it shifts the activation energy to the left. So now more particles fall into this successful collision area. So it's kind of like changing the curve. You know, your score didn't change on the test, but the curve suddenly got lowered, so now your grade looks better, even though nothing changed about your test. Increasing rate's a big deal in industry because it greatly reduces the time needed to make product, and it doesn't require a higher temperature. And increasing temperature is expensive. So if you can find a catalyst that costs less money than increasing the temperature to increase your rate, that's a winner. The other thing is that oftentimes increasing temperature decreases the amount of yield or the equilibrium. So again, catalysts are much preferred to temperature changes for increasing rate. A catalyst in a living system is known as an enzyme, and every biological reaction is controlled by an enzyme. So the opposite of a catalyst would be an inhibitor, and in a living system, then we would call it a preservative. And inhibitors work just the opposite of catalysts. They raise the activation energy. So again, it provides an alternate pathway that's more difficult. A couple other terms that you maybe have heard out there are biotechnology. It's a field that researches and uses the development of catalysts in everything from biological detergents to catalytic reforming of fuels to medical biosensors to cheese making. And catalysts are also important in something called green chemistry, since they can be reused and don't contribute to waste. Unfortunately, pollutants or waste from some reactions end up acting as catalysts in the atmosphere or in the water. So sometimes we have huge environmental damage from pollutants because they're acting as a catalyst. And the big example of this is the CFCs and the destruction they created with the ozone layer. The last thing to mention is this idea of the Haber process. It's also called the Haber-Bosch process, and it was developed in early 1900. And it's a big deal because it's a way to increase nitrogen fixation or make ammonia. And ammonia is essential for plant growth. It's fertilizer. So naturally in the soil, beans and some other things contain nitrogen-fixing bacteria, but it's a very slow process. And as you know, we approach 7 billion people. If we wait for Mother Nature to take care of the soil, we cannot grow enough food to feed the world. So what the Haber process does is it speeds it up. It uses a catalyst of iron, and it's a really big deal because 80% of the atmosphere is nitrogen, but as I've mentioned before, with that triple bond, nitrogen is really stable and really hard to get to react. But by using the Haber process, it has generated over half the protein found in all human bodies. So half the protein that makes you up right now is a result of the Haber process. And it's estimated to be responsible for sustaining a third of the Earth's population. So 2 billion people get to eat tonight because of the Haber process. And that number just keeps going up.